In this video, I'm going to look at some of the typical wavelengths of visible light, and maybe later on radio waves and X-rays. So I'm going to look at the typical wavelengths and so on. Okay, let me start with violet. Now for violet, let's see. Okay, let me just start by writing out all the a number of different colors in the visible spectrum. So that's violet, blue, green, yellow, okay, orange, and red. Now these numbers for the wavelengths are values that I've copied from Wikipedia. If you search for the words visible spectrum, you would be able to find a web page on these numbers. So the wavelengths of these various colors. So look. Now they are given in. I'm going to give them in terms of the ranges from violet. The range of violet, okay, goes from 380 nanometers to 450 nanometers. And the range of blue light goes from wavelengths of 450 to 495 nanometers. Green light goes from 495 to 570. And yellow would go up to 590. Orange up to 620, and red 750. So these are the typical wavelengths. If you're doing an A-level exam, physics exam, it's a good idea to have at least some knowledge of what these numbers are, or at least some rough idea of the numbers, because we need to know the colors. We need to know the colors of certain wavelengths. We need to know the wavelength of colors in order to be able to answer exam questions. Just one or two interesting things to note. If you look at the difference between the tracer numbers, you'll find that the yellow light seems to have the narrowest range of wavelengths. If you subtract the two numbers, is just 20 nanometers, and that's the smallest compared to all the others, I believe. If you look at the red light seems to have the biggest range of wavelengths. Okay. Now it's never easy to remember so many numbers. So what I tend to do is I can never remember the numbers in between, or not even the exact numbers at the two ends. But what I tend to do is I would roughly try and remember the rough values for the two extreme numbers. Okay. I kind of remember that at one end, at the bluish violet sort of end, it's about 400 nanometers. Okay, thereabouts. And on the other end, 750 maybe about 700. Right? I normally remember about the number 7. So if I can't remember the details, right, I would just remember between 400 and 700 nanometers. So the bigger number would be in the red end. So red color would be about 700 nanometers, and 400 nanometers would be the violet, or would be close to the blue color. Okay, so that at least means that I have an idea of what are the two extremes. So it's the red and the blue, or violet. And in between, hopefully it won't be asked in the A-level paper, but if they ask, we just have to guess if we can't remember this, right? But ideally we should try if you're sitting for the exam. Okay, now so the other things that I would like to write down are the corresponding frequencies and the photon energy. Now let me write down the formulae for these. We know that F lambda, frequency times wavelength, is equal to the speed of light. So if you know the wavelength, then of course we can calculate the frequency. So even in the exam, if you have remembered the wavelength, you could just use this and your calculator to calculate the frequency. But sometimes it's good to know, to have remembered at least a rough value for the frequencies. It sort of makes things faster and easier. So right, so that's a formula that you can use to calculate frequency from wavelength. And for the photon energy, that would be E equals to HF, Planck's constant times frequency, gives you the photon energy. Okay, so let's take a look at the typical values of this, just so we can be more familiar with it. Okay. So this, I'm going to make a frequency column. Now, there are two ways we can try and write this. One way is to write it in units of terahertz. Okay. So if it's that, I'm not going to write down all the colors. I'm just going to write down the two extreme, the two ends of the range. Okay, so this would be at this end would be 789 terahertz, right? That would be the, let's see, that's the higher end. Okay, and at the lower end of the frequency, lower end, this would be about 400 terahertz. So these are the two extremes, and again, it's useful to have an idea of what these values are. So it's of the order of 4 to maybe 800 terahertz. So that's one way to remember it. So let's write this down. So that's about between 400 to 800 terahertz. Okay, another way we can try and remember this, perhaps is to write the units of frequency in units of 10 to the power of 14 hertz. 10 to the power of 14 hertz. Let's see. So in 10 to the power of 14 hertz, this would be 7.89 times 10 to the power of 14 hertz, and that would be just 4 times 10 to the power of 14 hertz. So that's another way we can try and remember the frequency. Okay, so that would be about 8 times 10 to the power 14 hertz, and this would be about 4 times 10 to the power 14 hertz. Okay, so if you remember the units, if you prefer terahertz, the terahertz units, then it's between 400 and 800. If you find 10 to the power 14 hertz easier, then it's worth remembering that it is between 4 and 8 times 10 to the power 14 hertz for the visible spectrum. Now, for the photon energy, that would be HF. Okay. That would be HF. Let me write this out. HF. Now I'm going to put this in units of EV. Okay, in joules would be a very big unit, and the numbers would look extremely small. So I'm going to put it in EV. Now in this case, I'm going to write down the values of all of them, because we might actually need to have a better idea of this, not when we have to answer questions on emission spectrum of the hydrogen, and maybe on laser emission, stimulated and spontaneous, which I'll talk about in the maybe next 1 or 2 videos. So for the violet end, it would be 3.26 eV. So this corresponds to this frequency actually, or this wavelength. And that wavelength, maybe I'll go right to the bottom first. At the red end, the photon energy corresponding to this frequency, it's 1.65. Oops. Okay, I'm just using this line to indicate a marker. This line here, all the lines that you see here, they are not negative signs. Right? It's just a hyphen or just a dash. Okay, and the next one up, the red range of red photons is between 1.65 and 2.00 eV. Okay. Orange photon will be between 2 and 2.10 eV. Yellow would be between this and 2.18 eV. Green, okay, green 2.30. Blue go up to 2.76. Now again, you may not need to remember the exact values of this. I think it's good to remember one set of values, either wavelength, frequency, or photon energy. And I would personally maybe just remember the wavelengths, because it seems that these are used or expressed in terms of wavelengths quite often, at least in A-level physics. And we can always use these two formulae to convert from wavelengths to frequency and photon energy if necessary. So for example, how might knowing about the photon energies be useful? So let's take a look at an example. We'll see some examples later on laser emission, but if you look back at an earlier video in which I talked about the hydrogen atom, okay, you might remember that I talked about when I talked about hydrogen, the hydrogen energy level. Okay, that's the hydrogen atom. There are many levels. Right, let me try and draw, say, the energy axis. Let's say that that's the zero level. Let's say this energy is in EV. Okay, it's in EV. And now at the lowest level, at the ground state, or the innermost orbits of the hydrogen atom, the energy is minus 13.6 eV. Right, that's right, minus 13.6 eV. That's the lowest innermost orbit, the lowest energy level. The next one out, the second orbit has an energy of minus 3.4, and the next one out, third orbit has an energy of minus 1.5, and you get lots and lots more orbits, which are squeezed closer and closer and closer together as it moves towards zero. Okay. Now I have over many videos talked about the transition between this, and specifically I've talked about the emission spectrum of hydrogen in the visible light. And if you remember that line spectrum, the transition from the third to the second level is red light. Okay, and the transition from the fourth to second orbit, or second level, is light blue. And the next one is from 1, 2, 3, 4. Let's see. 1, 2, 3. Okay, I'm not drawing this very clearly. Let me try again. Light blue would go from that one, the fourth, to the second, and blue goes from there, that one, to here. Okay, so now in an exam question, for example, we might see a question that asks that in which these energy levels are given in EV, and we might be asked, for example, to say what is the color of the light that is emitted when the electron falls from, say, the third level to the second level. There are two ways we can do it. If it's for the hydrogen atom, ideally we would have memorized that this is red light, and that's it. Okay. If not, or it could be the question might not say hydrogen atom. It might just give you some arbitrary, some energy levels without saying what atom it is, with the energy values. Then we would then need to actually subtract the numbers to determine the photon energy, and then to think about what the color is. So in this case, if I look at these two numbers, just by looking at these two numbers, if we subtract this, if I subtract these two numbers, let's see, the difference is about 2. Okay, it's 1.9. It's 1.9 eV. Then we have to think, 1.9 eV, a 1.9 eV photon. What color is that? Okay. Now there are, hopefully we would have remembered that 1.9 eV is in the red color range, because from this table, this column of numbers, see that red is between 1.65 and 2 eV. Okay, and 1.9 is in between. If you have not remembered this photon values, energies in terms of EV, then hopefully we might have remembered the wavelengths. That red light is about 700 nanometer, and then we can use this formulae to calculate the wavelengths from the photon energy. And if you find that it's close to 700 nanometers, then you would know that this transition from this level to this level gives us red lights. So this is an example of how we might need to use the wavelengths or the photon energy. So it's always good to remember some of these. Okay, and if not all the numbers, at least the two extreme ends. But ideally, we can remember at least one set of this.